how it's going.
Sure.
Um, we can talk more. But all right, well, what I'm going to do today, I'm going to post some more introductory type videos, and I'm also going to post these lecture notes. So there's a lot of definitions and theorems within this unit, and I'm not going to spend a whole lot of time at this point talking about them. What I'm going to do instead is just work through a few exercises from the first couple sections in this unit, and then kind of go back and reference those definitions and theorems that we'll need for the exercises. Does that sound okay?
Yeah, yeah.
Okay, okay, so I hope to post some videos and stuff today, and then I'll finish up this discussion tomorrow, and then tomorrow I should have some homework and quizzes posted for you to work on, working towards next week, I guess. So yeah, what we're going to be talking about in this unit is number theory, and so we're just going to be studying integers and their properties. So this is actually my favorite part of the class, so I'm really excited to talk about it. So we're going to be talking about divisibility of numbers, prime numbers, talking about binary, hexadecimal. Have you dealt with binary in other courses?
Yeah.
Yeah.
Machine language. Yeah, I have.
Yeah. So yeah, that's great. That's what's cool is, a lot of you have seen it, and so I'm hoping to kind of touch on that and expand on it a little bit too. And so yeah, that'll be fun. And I guess I like number theory because I think it's really beautiful. But there are actually some interesting applications that a lot of the people in this course seem pretty interested in. I think the main one that people talk about is cryptography, and so there's a nice video on Khan Academy about the basic ideas of cryptography, and so I think that'll be kind of fun for us to explore a little bit. And there's other applications of congruences and these modular arithmetic things that we're going to be talking about, and so one of the examples is with like a check digit. So if you've got a series of numbers in some code that you're trying to put on like a product or on even like an actual check, if you want to make sure the numbers satisfy, I wasn't going to talk about this because I don't know how to explain it very well, but then I started talking. But yeah, if you want to make sure that your digits satisfy a certain property and it's kosher with your thing, but you don't want to make it public, you can have like a check digit within these sequences of digits to check on that. And so we'll talk about that application too. And it's pretty straightforward after we learned these basics. And even some of the cryptography stuff was kind of intimidating to me when I first started teaching this class because I didn't know anything about it. But what I did last semester, I had students who this is kind of their area of study, and they did some presentations, and it's really kind of some straightforward examples based off of what we're going to learn. So that's kind of exciting that you can get started in that area too. Are you familiar at all with cryptography, or have you studied it at all in other courses? Or
No, not so much. I mean, I've had experience with it in my military career, but
sure.
not direct practical application or as far as getting into the weeds on it.
Yeah, and we're not going to get too into it, but it is. I think it is exciting that these ideas are the foundational ideas for it, and so if you did go on to study it, you would have kind of a leg up here on these basic ideas, and we might, throw in a couple examples in homework or exams just to kind of see the applications of these properties. So I think it'll be interesting. So let's see. So yeah, some of the things we're going to talk about, and I kind of mentioned it, but divisibility, the division algorithm, modular arithmetic. We're going to be representing integers, like we're talking about binary, hexadecimal, octal, decimal, and greatest common divisors. We're going to be using the Euclidean algorithm. This Chinese remainder theorem is pretty cool. It allows us to solve a system of congruences, which are basically kind of like a system of equations, okay? So congruences probably doesn't sound very familiar right now, but we're going to get into that today. So uh, yeah, so I think what we'll do is start with section 4.1, and if you don't have the textbook, I think this presentation after I post it will be pretty well explanatory, or pretty well explain everything from the section, the definitions, the theorems that you need to know. So don't, if that section 4.1 doesn't make any sense to you, don't worry about that. So what I want to do, yeah, so I want to just look at an exercise and kind of go back and talk about, if I can find what I did with my book. This is not good. Okay. Oh, it's hiding under my notebook. What do you know? All right, so I want to start with exercise 6 from section 4.1. So I think this has to do with divisibility, maybe, or I meant it to. Okay, so this is actually a proof. So I think what I want to do before 6 is I want to talk about number 1 first, so that we're on track with that. So number 1 from section 4.1, we're talking about does 17 divide each of these numbers? And the definition of divisibility is a little bit different than what you're used to with just division, okay? When we're talking about a number dividing an integer, we want to make sure that it goes in there evenly. So let's see, if we were talking about 34, I could write, this is new notation, and you might have seen it before, I can write 17 divides 34. And you read this, 17 divides 34. Okay? Have you guys seen that at all?
No, I haven't.
Okay, good. So new notation. And so it's important to remember that this is a relationship. This is a relationship between two integers, whereas 34 divided by 17, this is like an operation, okay? So it's kind of like when we were talking about propositions and variables, like variables within an algebraic sense, like with equations. You know, those variables could take on a value of real numbers, where our propositions took on a truth value of true or false, and that's true with this division, this divisibility relationship. So this notation here is either true or false. It doesn't have a value, so it doesn't make sense to say 2 here. It only makes sense to say 17 divides 34 is a true relationship. Does that distinction make sense?
Yeah, I was just trying to get I was looking at it differently. I was seeing when I saw 17, and then I didn't know if that was a parallel sign or a slash sign.
Yeah, good,
Yeah.
exactly. And that's what's tricky, because if I just slant it a little bit, if I say 17 divided by 34, this means, 1/2, right? But
Yeah.
if I have, yeah, and my writing's maybe not the greatest, but if I have just an up and down
No,
slash
you
like
did it
this,
just fine. I jumped to an assumption that
right?
just didn't slant it because we were talking about division.
Yeah,
So
exactly.
I'm glad I
Well,
clarified that. Okay.
yeah, me too.
I
Me too.
can
That's a
find-
great, yeah, that's an important distinction, because a lot of times when I present problems on this divisibility idea, I'll get numbers back, and it just doesn't make sense to talk about numbers here because it's a relationship. So yeah, you want to make sure that you have a distinction between these three, those three little symbols there, and that's going to be helpful in your writing too, to keep in mind. Make sure that that slash is clearly, up and down, so that your reader doesn't get confused and think you're trying to divide something. Um, and so the order of this is important too. we wouldn't say here, we wouldn't say, let me try, we wouldn't say that 34 divides 17. Okay? And that's because if I take 34 and divide it into 17, I'm going to get a fraction, right? If I
Yeah.
take 34 and divide it into 17, I get 1/2. Okay, so this order is a little bit confusing. The way that I always remembered it when I was first looking at the definition is that the bigger one is second. Um, and I think if you read it as it's to be read, with the divides, I think you can kind of see it. So in my head, when I see this, I write 34 over 17 is equal to 2. Okay, then I know it's a true relationship because it's an integer. Whereas this is false because I don't get an integer. I get 1/2 when I do that division. Does that idea kind of make sense?
Yeah, because I mean, I'm following along with you. I'm also looking at the book, and I'm seeing that
Yeah.
what we're talking about. Okay, we end up with an integer, a whole number, and as opposed to 2.75, which is not an integer.
Yeah, exactly. And so we go to a fancier definition, right? Because we're going to be talking about this relationship with just general integers. So we might not have specific values that we're looking at. We might just be talking about some properties of divisibility. And so this definition is nice if we're talking to more generally. And this is going to come up when we move to modular congruences and that Chinese remainder theorem. So this idea of divisibility is kind of important to keep in mind throughout the whole rest of this section. Um, so yeah, this is a more specific definition. We've got two integers and A divides B if I can rewrite B as some multiple of A. And so if we look at our example of 17 divided by 34, or I said that wrong, that's not good. 17, we're like trained, divided by.
Yeah.
17 divides 34, that's how we read this. A divides B. And so this is true because I can write 34, that's like my A, right? No, it's like my B, sorry. It's like my B, as 17 times 2. So since 2 is an integer, we're good. So I think this definition is a little bit tricky to understand. I like to think about it like 34 divided by 17 is, I mean, it's the same idea, but I like to think about it like that if I'm trying to test divisibility. And so, yeah, just keep in mind that order is important. 34, and we say does not divide 17. And then that distinction of the notation there between division and divides. Okay, so what I want to do now, I think we're ready for 6, actually. I think it'll be a good jump because we're going to go from this specific discussion on divisibility, and we're going to talk about this property that holds with general integers. So I'm looking at this and thinking, is this a good idea? But we're going to try it because there's another theorem that might be good to start with. Yeah, I think I'm going to start with a different theorem, and then I'll talk about 6. Let's see. I didn't really know how this would flow, so I kind of have a bunch of different ideas, and we'll try to find one. Oops, where's that theorem at? Where are you? Well, let me just write it out. So I'm looking at a theorem on divisibility. It's right after it's introduced, and I'm gonna prove one of the parts that's not presented in the text. So this is just a theorem, and one of the parts is proved in the book, but I'm going to do one that's not proved. So we've got A, B, and C are integers. And A is non-zero. And then I have some properties. So if A divides B and A divides C, then A will divide the sum of B and C. Okay. And I think this makes sense. 2 divides 4 and 2 divides 6, this tells me that 2 divides 10. So kind of makes sense, but it's proven in the text. I'm going to prove the next one. So property 2. Does that property 1 make sense to you guys?
Yeah, what you've explained so far, yeah.
So far, okay. So property 2 is the one we're going to prove. And maybe I'll leave you guys to prove property 3. So if A divides B, then A divides BC for all integers C. Okay, so I'm going to do a proof of this. And I'm going to do a direct proof. So I'm going to be starting by assuming that A divides B. So I'm going to say let A, B, C be integers where A is non-zero. And that's going to come up a lot when we're talking about divisibility and doing different proofs within divisibility, because, you know, division by zero is undefined. So we've got to include that. And so let's see. So let's assume A divides B. And then once I start with that assumption and I've got some divisibility property going on between some of my values, I'm going to go ahead and just rewrite that relationship with using the definition. Okay, so remember the definition just says that I can write B as some multiple of A. So I'm going to say then by definition of divisibility, B is equal to A. And I'm going to be careful here because in the definition it has a C, but I'm going to write a K here just to make sure I use a different integer where K is an integer. Okay. All right, so then I want to try to figure out something about BC. Okay. Right now I just know something about B. So let's think about where we want to go for a minute, okay? If A divides BC, then BC can be written as some multiple of A, okay? So we've already got this relationship. Can you see how to change it to get to here? Any ideas?
Sorry, I was writing notes.
No, that's okay. And if you don't see anything, it's okay. Take your time.
Okay, well, we're talking that BC, no, A is a multiple of BC, right? That's what we're saying? Because
Um,
it can be divided by A.
so right, so B, from this assumption here, we know that B is a multiple of A. And that's what we've written here. We take A, multiply it by some integer, and that will get us B. Just like 2 divides 10, right? This is because 10 is equal to 2 times 5.
Right.
So we're able to write out,
Okay.
yeah, yeah.
Got it backwards.
Yeah, I've done that for years, and so every time I see that definition on the side, I always just write out a specific example that makes sense to me, so I get that order right. So, like on my side, I'd write down, okay, 2 divides 10. I know 2 divides 10. That's because I can write 10 as 2 times 5, and that helps me keep that order straight. Because yeah, you'll get it mixed up. Okay. So let's see. So we're trying to find out something about BC. We know something about B. So how do we go from B to BC?
It's right on the tip of my tongue. I'm,
Yeah.
I'm looking at something. It's something really simple too. It's because I'm thinking almost algebra, like as
Yeah.
in I
Is yeah.
need to relocate something here because we're trying to find out a. We know b, so then we have a times some integer, so we would need to divide some integer by each side or multiply by no divide by each side in order to find out a, as in k over b equals a.
Okay, you are on the right track. There's some algebra that we have to do, and you said it in there when you were thinking through a bunch of different ideas, what we can do here, because we're trying to get this equation, right? We're trying to show that A divides BC. So if we want to find out something about BC, what we can do is multiply both sides by C to get BC is equal to something. So let's just see what happens when we multiply by both sides by C. Do you see it, kind of?
No, I was saying you should get a chat window there too, right? Colin just
Oh, oh, good. Colin, I thought you were bored and you left, and I thought, oh no, I hope this is not so boring. Because at least if I record it, then you guys can just like fast forward and you Mic isn't working. Okay, okay, Colin, thank you. Oh, good. So, all right, so we're gonna uh, multiply both sides of this equation by C to obtain, yeah, BC is equal to AKC. Okay, alrighty. So actually now we're done. We need to wrap it up and be clear that we're done. But what we were trying to show, remember, we were trying to show that A divides BC. And what we've done now is written BC as a multiple of A. Because, C is an integer, K is an integer, I know KC is an integer, so it satisfies the definition of divisibility here. So I'm just going to say, to wrap that up here, I'm going to say since KC is an integer, this shows A divides BC. And that's it. And I think maybe if we do a specific example, I should have done a specific example here before I went into this. I think a specific example is more obvious than these general, more abstract variables here. Let's see, 5 divides 35. And then I know 5 divides any multiple of 35. Is basically what it's saying, right? 5 divides 70, 5 divides 140. Do you see that idea?
yeah.
Okay, good, good, good. This has made me a lot better at algebra and factoring, all this number theory stuff, because it really helps you think about factors and all that stuff. So if you're going to do some factoring, this is good work for you. And that's it. That's our proof. So see if you can do part 3. I don't know, we could prove part 3, but I feel like maybe we want to go on to something else here. Let's go on to something else. Let's go on to that other proof, the number 6 I started and then decided to change, because that one's a little bit more exciting for you guys to see. I think if I can think of it, or let's see here. So number 6, we're trying to show if A, B, C, D are integers and A is non-zero, such that A divides C and B divides D, then AB, oopsies, then AB divides CD. Okay, so we want to prove this. So let's look at an example here. We've got four distinct integers. Well, not necessarily, but it'll make more sense if we do four distinct integers here in this example. And let's see, we've got 2 divides 4, and 7 divides 35. So what this is saying is that, therefore, I know that 14 divides 140. Hopefully I did that multiplication right. So that's the idea that we're trying to prove here in a general sense. Does that example make sense, guys?
Yeah, I was already laying out in
Doing
my head the if P then Q. So
good. Yeah, good, good.
yeah,
Okay, so we've got,
and
yeah,
B and D and all. Yeah, sorry.
good, good. Yeah, so we've got an implication here to prove, and so we can use a direct proof, right? So we can, well, we can try. uh, and you know, a lot of these proofs with divisibility and modular congruences that we're going to be doing are pretty straightforward. They're not crazy contradiction cases, stuff like that. It's pretty much just assume the hypothesis, apply definitions, apply theorems, get your conclusion. So keep that in mind. Not to say that all that work that we did was wasted. You'll see a lot of those proofs maybe in small doses, but so always start there in this unit. Try to assume the hypothesis, think about all the definitions and theorems that you have to use, and then try to get to your conclusion. So I've proved this before, but it's kind of left me, so I'm hoping that it goes okay, but I'm gonna, so this is good real live thought process here. I'm going to do an outline instead because I'm not sure on my strategy here. So I'm going to start off by assuming that A divides C and B divides D. Okay, if I know that, I'm going to use the definition to rewrite this, because remember, this is just a relationship. I can't really manipulate it. I can manipulate it with that theorem that we were just talking about, that three-piece theorem. If you're wondering what I'm talking about, it's page 238, theorem 1 from section 4.1. And so we could apply some of those properties, but I don't know, all of the hypotheses on that theorem makes the divisibility, like the A, be the same on both of them. But this one we have A divides something and B divides something, and so in that particular theorem, it doesn't really help us out that much. So I'm just going to try to think about the definition and trying to apply the definition of divisibility here. Divisibility. Okay, so I know that if A divides C, okay, remember, write out your example so you know which one to start with. Remember, the bigger one is always second, so when I'm writing this out as an equation, I always start with C and write it as A times some integer. So this is saying C is a multiple of A. A divides C. So this tells me that C is some multiple of A, where L is an integer. Okay, and then let's write out B divided by D. This means D is some multiple of B. And then just careful with your variables. You got to make sure that you're introducing new variables that you haven't used any before. Otherwise, it wouldn't make sense. Okay, so let's think about, when we're trying to work through this proof, we always want to think about where we're trying to go. Where I'm trying to go is I want to know something about AB dividing CD. So in other words, I want to rewrite CD as some multiple of AB. Okay?
Okay. Yeah, I got it.
Okay, and it's just algebra, right? Which is
Yeah.
so many of these proofs, we just have to apply some fancy algebra techniques after you get over the logical hump and like how you're going to start it. Once you get all your information together, then a lot of times it's just algebra that you have to do. Um, so what we can do um, is, uh, any ideas out there? Not really?
No, 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 not at the moment. I'm still writing.
Yeah, that's okay. Yeah, take your time. Let's take a moment. I saw the idea here, and then I kind of started going faster because I thought, oh, good, I know how to do it. Sometimes, because sometimes I don't. So that's always scary. But
Hmm.
are you thinking out there, Colin?
Yeah. I switched back to
Yeah.
my other laptop because we had a Windows update, so everything broke. But
Oh
I
no.
fixed it. I fixed
Oh,
it, so now it's working. But
good.
um, hmm. Oh, this is so easy because it's just
No.
algebra, but it's like so complicated to explain it.
Yeah, no, I don't think it's easy. I didn't see it, until just a bit ago. So, and that's because I've proved this before. So that's the
Yeah,
only reason
so
that I saw it. So, yeah, I don't know.
yeah. So what is up closer to the top? You put CD equals ABM.
Yeah, yep.
Okay, so M could be L times K, wouldn't it? Or it could be.
I think you've got it. Yeah. Um, yeah, I think you've got it. We just need to take that vision and write it out, so that we can see how you got to LK. Because I think that's what it is, but I'm not sure. Um, because the only things that we can really use here are these equations, right?
Right.
And so what I'm thinking is, just like in the last one, multiplying both sides by something. Because I want to get CD. I could do this with either of these equations, but if
Mm.
maybe I look at this equation and multiply both sides by D, and I'm still not quite there yet because I want to know something about AB, and right now I just have A and no B. So, any ideas, Colin or Sean?
No, I'm drawing a blank, man. I'm looking at it and it's just I'm not getting it.
That's
That's,
okay.
that's
What do we know about D?
Oh, so okay, so you substitute D for BK because D is equal to BK, and then you can also substitute. Oh man, that'd break it, wouldn't it? Oh
Yeah.
no no no! So then you substitute C by
Oh, we don't
AL. Wouldn't
we
you
don't need
need?
to do that.
No.
Yeah.
Okay.
You got it, though. You got it. Once you see it, I think, once we write it here. So we're
Oh
going
no! Oh oh oh! My brain it exploded. It's
Whoa! This is
everywhere.
great. This is great.
Hmm.
Brain explosions. Okay. So we're going to write, just substitute on one side, AL, BK. Okay. And now we've got CD written as, multiplication is commutative. I can do it, and associative. I can do this in any order. So LK, just like you thought.
Okay,
Um,
I see it.
do you see it, Sean?
Yeah, I just I'm overthinking it. That's fine.
Yeah,
Keep going.
yeah, yeah. I think we get all these symbols, equations going, and then, yeah, it's pretty easy to overthink it. That's no big deal. So now we've shown that AB divides CD. So maybe, this is the outline here. Do you guys think it would be helpful for me to write it out? Is that a helpful practice, or is this, sufficient, or how you guys feeling? Because I know that there's some questions about like write-up of proof, so maybe it wouldn't be a waste of time. What do you guys think?
Um, how many more proofs do we have to do with this sort of
Oh,
thing?
today?
Yeah.
Uh, oh, well, I have like a bunch of slides. So,
Okay.
but I only plan to go for like an hour, and
Right.
I'll either record the remaining tomorrow, and then after that, if we run out of time, because I don't want to talk much longer than that, because we'll like reach our maximum.
I
So,
I think it's important to stick with doing the concepts. The proofreading, we've covered it. We're in the middle of an assignment on it, and
Yep.
that,
yes.
if we have questions, we can follow up with you and say, hey, okay, I get the theory, but I'm having a problem applying it to a theorem.
Yeah,
And that's it.
yeah, that's great. That's great. Okay, so let's see. I think the other problem I was talking about trying to do is number 14. Okay, good. So now we're going to move in from divisibility, which is a concept we're going to apply for the next thing. We're going to be talking about modular arithmetic and modular congruences. And so before we get into that, I think we need to talk about the division algorithm. So what I'm going to do is talk about exercise 10, and we're looking for quotients and remainders, okay? So we're going to be dividing like today. Um, and and so I think before you go into this, keep in mind the positive integers are pretty straightforward. The negative integers get a little bit confusing, okay? So kind of really try to think through that when I present a couple here. And again, there's going to be more examples in the slides that I post, so don't freak if these don't really click. The division algorithm is not actually an algorithm. I do not know why it's called the division algorithm, but it's actually just a theorem. So it's just saying that, let me write it out just so that we've got it here. So we've got a is a positive integer. Let a be a positive integer. And then there are unique integers Q and R with, so R's our remainder, okay? And I'll define these terms and stuff here, such that A is equal to DQ plus R. Why is it saying A is positive? Okay. Do you guys know what an algorithm is, probably?
Yeah.
Yeah, just like a sequence of steps that we follow to complete some task, right? And so this doesn't really tell us how to find these things. It's just like, it's actually a theorem, but it's always called an algorithm. I don't know. So what I want to do is a couple examples here of this to get these terms straight here. Because each of these has a different meaning. This is our dividend, so it's what we're dividing into. This is our divisor, and when we put some specific numbers in here, these will make more sense. This is our quotient, and this is our remainder. Okay, and this is written out prettier in the notes, so this is kind of crazy looking. But so what I'm going to try to do is understand what happens when 19 is divided by 7. So I want to know the quotient and remainder, okay? Because this is getting towards, we're moving towards modular arithmetic and modular congruences. And what those have to do with this is that we're concerned about that remainder, okay? So we're looking under different moduluses, which is like different divisors, and we're considering the remainders and how these numbers are related to one another. Okay, so let's go back to long division and I think that all these terms will make more sense, maybe. So what I'm going to do is take, okay, 19 divided by 7, okay? So let's put out these terms here so we get used to it. This is our dividend, and 7 is our divisor, okay? All right, so 7 goes into 19 2 times evenly, okay? So that value without any remainder or decimal places, that's our quotient, okay? So our quotient in this case is going to be an integer, okay? But it doesn't go in there evenly, right? We've got a remainder. 7 times 2 is 14, so our remainder is 5. Okay, does that long division look familiar? Sometimes that helps, sometimes it doesn't. I don't know.
Yep, all I need is a picture. It's in my head.
Good, good, awesome. Okay, so what this theorem is saying is that this relationship exists. If I pick out, you know, if I pick out 2 integers, I can find this relationship. I've got a quotient and a remainder. And so what we're going to be doing is moving from this kind of long division look that we're pretty familiar with and writing this information out as an equation that we can manipulate. And this is going to be helpful when we're talking about congruences, because we're going to be writing out these modular congruences in this sort of way, okay? And this division algorithm idea will come through in a bunch of different places. We're actually going to use this to convert decimal integers to binary. Okay, there's kind of a cool application there. We just divide by 2 successively and look at the remainders. I like that little trick. And we'll also be using this to, this is going to sound crazy, but we're going to be writing greatest common divisors as linear combinations of inputs. So it's going to be important. Those things seem like crazy high in the sky, but it's going to be important to get this foundational idea here with these equations so that we can apply this idea in more complicated situations, okay? So if we write out this long division thing, all it's saying is that I take 19, I take my divisor, which is 7, I multiply it by my quotient is 2, and I add my remainder. Okay? How's that look? Does that make sense, guys?
Yeah, first time I looked at it, I realized that the definition was basically just taking what we've known from long division and spinning it so it's the other way around. So.
Yeah, exactly. Yep, exactly. Just writing it in a different way. Let's see here. So what we want to do is, let's talk about these 2 functions, okay? Now, it's going to be important to remember that these 2 things I'm going to talk about now are functions and not relationships, okay? Once we get into congruences, we're expressing a relationship, okay? When we're talking about the mod operator, we're getting some output back, okay? It's kind of like multiplication, division, that sort of thing. So if I say 19 mod, okay, mod 7, this just means if I take 19, let me write it out. I take 19, divide it by 7, what's the remainder? And you've probably seen this mod operator maybe in your programming stuff. Does it look familiar?
Well, the languages that I've been using, no, but
No?
I understand the concept.
Because I think sometimes it's like the percentage, sometimes it's denoted like that. I don't know. Yeah, probably in your language you have it's a percentage in your language, Colin? Okay.
It's really gross.
It's gross?
Yeah, it's not the funnest.
It's not the funnest. In what way did you apply this in your class? Do you remember?
We just had we had to make a small calculator where it was like find out. It was essentially a true-false calculator where it was did it divide into it evenly, and if it didn't, find out what the remainder was.
Yeah, exactly. So yeah, so we can use this mod operator, like you said. If it divides evenly, your remainder is going to be 0. If it doesn't, then you'll have a remainder, a non-zero remainder. So yes, there must be more fun applications of this modulus operator, but I don't have any right now. I'll have to work on it. I think there's some cool videos I'm gonna post, and hopefully we'll find some interesting examples there. But okay, so 19 mod 7 is 2, because no, it's not 2. It's 5. Okay, so that's because if I divide 7 into 19, I get 5 left over. Now the other operator is div, and we won't use this as much, but this is just saying, how many times does 7 go evenly into 19? That's 2. Okay. Okay. So those are two functions that we're going to be talking about. And those are really easy to calculate by hand if you have this equation written, okay, if you have the division algorithm applied. Let's see. So we've got those down. Let's look at another example with positive integers. Can you guys see? Oh, this is kind of a cool one. Well, maybe not. Let's try what happens when 44 is divided by 8. So I want to write this out in terms of the division algorithm setup. Can you guys see how to do that?
You're talking about, we're talking about using one of the two functions, write it out accordingly? Or
Yeah,
you
so
the algorithm?
yep, I want to write it out in this way with the quotient and remainder.
It'd be 44 equals 8 times 5 plus 4.
Yeah, exactly. So we've got our dividend, we've got our divisor, our quotient, and our remainder. Okay. Does it make sense where that came from?
Yep.
Sean, is that okay? Yeah? Okay, good. Okay, so now that I've got this equation set up, I know 44 mod 8 is 4. Okay, I know 44 mod, oops, nope, div, yeah, div 8 is 5. Okay. All right, let's do a negative value. And I'm curious now because in the book it states that A has to be positive. So I don't know what that's about. I'm going to do a little bit of work, but we can definitely manipulate it and update it to have negative, but I don't know why it does that. So all right, so I want to take negative 123 and divide by 19. Okay. So the thing to remember with the division algorithm is that our remainder is positive. Okay, so that's the issue that comes up with these negative values, because instead of just dividing it and then adding what's left over, we actually have to kind of go over, but really under the negative value. Okay. So I think you'll see what I'm talking about here. So that's the only condition that causes us trouble here with the negative values, the negative dividends, because our remainder has to be positive. Okay. And keep in mind, if you're in Excel, there's a mod and a div operator. On Wolfram Alpha, there's a mod and a div operator. Okay, so this is ridiculous. I understand these calculations, but the calculations will be important to understand once we get to this Euclidean algorithm, Chinese remainder theorem, writing out a decimal number in terms of binary. Okay, so I understand that this is silly, but keep in mind that it will be important on your assignment when you're instructed to like find the quotient or remainder, make sure you do it by hand. I think you should definitely check it using Excel or Wolfram Alpha, but you know, keep in mind that you want to be able to do it by hand because you're going to be kind of forced to in further situations. So, so I know that I want to rewrite negative 123 as some multiple of 19. And so for sure, my quotient is going to be negative. But I want my remainder to be positive. So what I'm going to do is just use a calculator, and I'm going to take, I'll take 123 divided by 19. So I get 6.5 about. So what I'm going to do is take negative 7, okay? Because I want to go over and have a positive remainder, okay? So I'm going to take negative 7. Oh, now I need my calculator again. Oh, I shouldn't. I can do this by hand. 63. 6 and 7 is 13. Okay, so plus 10. Now, this is confusing because look, if I was trying to take 123 divide by 19, what I'd do is I'd undershoot it. So I'd say 123 is equal to 6 times 19, 54, 111. So plus 13. No, plus 9. Plus 9. Oh, cool. Now you're seeing some relationships between these remainders. See how the remainders add to 19? That's always going to happen with the positive and negative. The remainders will add to 19. Do you see the difference there? Are you guys confused about the negative thing? We just have to make sure that the remainder is positive. So that's why we have to think about it a little bit differently.
Yep, it's cool with me.
It's cool?
Mm-hmm.
Sean, how you doing?
Yeah, I get the whole shooting under thing because you're identifying the remainder.
Okay.
I had to go and relocate my dog. He was snoring in the background. It was driving me nuts. So I missed the part about. Sorry, I missed the part about the negative and the positive part.
Oh, okay. Yeah, we'll touch on that more, but if you've got, so like let me look at this example up here. From this example, I know that negative 19 mod 7 is going to be 2.
Oh, wait a minute. Okay, wait a minute. Okay, I'm with you now.
Okay.
I see it. Negative 19. So yeah, if you're going to do, I can see. Yeah, I get it.
Cool. All right. So that sometimes, because sometimes people really have trouble wrapping their head around doing this with a negative, so you could do it with a positive, and then just subtract it by your divisor. Subtract that from their divisor. But you still need to know how to write it out like this. So it's something you probably want to get comfortable with. So you'll be fine. All right, so this tells me that negative 123 mod 19 is 10, and negative 123 div 19 is negative 7. Okay? All right, so I think that we're good on that. Let's move into, are you guys good maybe for like 15 more minutes?
Oh, yeah.
Okay,
yeah, totally.
Okay, I just want to go into modular congruences here before we stop. So let's see. Actually, let me write out this stuff with a modular congruence, okay? So remember, a modular congruence is going to be expressing a relationship, okay, between two values. So if I want to express this with a modular congruence, I can say negative 123 is congruent to 10 mod 19, okay? And so notice how that relationship expression is different than the function expression, right? So this is our function, our operation that's happening, where we get some output, and this is a relationship between. It looks almost the same because we've got mod 19, okay? And so we can interpret this relationship in terms of this function. This just means that negative 123 mod 19 is equal to 10 mod 19, okay? So if I wanted to speak generally, I could say, okay, let's say A is some integer. Let's say it's congruent to 10 mod 19. That congruence is just saying that if you take A and divide it by 19, you get a remainder of 10. So there is an infinite number of possibilities for A. A could be an infinite number of values. It could be 29. It could be, you guys see another value that it could be? It could be 10. I took an easy one. Okay, how are you doing? Any ideas? What else could A be? Maybe let me write this out. Is it being, so this means, I can write this in another way. This means that if I take A, if I multiply 19 by any integer, this is how I can write A. I take A, multiply 19 by something, and add 10. I think that might hurt. I don't know. Let me, maybe let me write the definition of a congruence here generally, and then that might help. Let me write one more thing. Uh-oh. Where'd I go? There we go. Okay, let me write this definition and see if it helps, okay? Yeah, I don't know. Sometimes the definitions are more confusing than helpful, but let me just copy, actually. See this definition, guys? It's kind of gross. I don't know. I think it's easier for me to think about, let's see. So I was saying that, let me try another example that's easier to see. I know that 12 is congruent to 2 mod 10, okay? And that's just because if I divide 12 by 10, I get a remainder of 2. If I divide 2 by 10, I get a remainder of 2. Okay, so we can think about this in terms of the division algorithm. 10 times 1 plus 2. 2 is equal to 10 times 0 plus 2, right? So all this congruence is saying is that those remainders are equivalent, okay? And so I'm telling you this in the hopes that it helps. But I will tell you, when I first learned about congruence relationships, I did not understand this relationship because all I focused on was this definition, which didn't quite make sense to me. You know, so I really want you to understand that idea that those remainders are the same, and that's why they're congruent. But we can talk about this definition too, because this definition is what we're going to be applying when we are trying to deal with these congruences and proofs. So it's a good thing to understand, but I just want you to understand this more general idea of having the same remainders. How are you guys feeling about that? Does that make sense?
The physical representation there, that helped me out. I could see the relationship there more than the words.
Okay. Colin, how about you? Is that making sense?
Actually, I just got it right as soon as you asked.
That's good. I'm glad I paused. Okay, good. All right. So let's look at this definition. We've got A is congruent to B mod M if M divides A minus B. Okay? M divides A minus B. Okay. So let's think about why this makes sense. Let's look at this example. So this is saying, if I write this out in terms of definition, this is saying 10 divides 12 minus 2. Okay. Oh, I thought of it. If they have the same remainder, then subtracting those guys will give us a multiple of 10. What do you guys think?
Yeah, that's how I got it.
Okay.
Yeah.
So 10 divides 10. Okay. Let's do a more complicated example to see this more clearly. Let's say 37 is congruent to 22 mod 5. Because if I divide 37 by 5, I get a remainder of 2. If I divide 22 by 5, I get a remainder of 2. So I know this congruence holds. Are you guys convinced that that congruence holds before I go further?
Mm-hmm.
Yeah?
Mm-hmm.
Colin, are you convinced?
I'm putting my faith in you.
Hey, no, that's not a good strategy. Trust me, I make too many mistakes. Let's write it out just to be sure. So 37 is equal to 5 goes into there 7 times. We've got 2 left over. 22, 5 goes into there 4 times. We've got 2 left over. So if I take 37 mod 5, I get 2, and 22 mod 5, I get 2. So this congruence makes sense. Okay, so now look, 5 divides 37 minus 22. 5 divides 15. So that's good, right? It satisfies the definition. Maybe let's look at something that's not congruent. Let's look at, I know that 21 is not congruent to what? Is not congruent to, let's go, 34 mod 3. Because I know the remainder, I know that 21 mod 3 is 0 because 3 goes into 21 evenly, so there's no remainder. I know 34 mod 3 is 1 because 3 goes in there 11 times, 33 remainder 1. So this congruence should not hold. So we can see if I take 3, I want to know, does that divide 21 minus 34? And it shouldn't, because I know this congruence is false. 21 minus 34 is negative 13. So yeah, 3 doesn't divide it necessarily. However, look, if I did 21 is congruent to 33 mod 3, I know this is true. Let's see what happens there. 3 divides 21 minus 33. 3 divides negative, negative 12. Yeah, so that's good, right?
Right. Yeah, I see it.
Okay, so kind of soaking in this idea of congruence, okay? And there's properties and stuff that you'll see in the handouts, but I just want to do 1 or 2 exercises here. Oh, did we get sidetracked? I think there was a question here a while back, and then we left it. So let's go back to it and see if we can figure it out. Oh, here, this was it. So we were looking at this integer a. We didn't know anything about it other than that it was congruent to 10 mod 19. Okay, so I have listed a couple of values, and I took the easiest ones that a could be. So anyone have another value that a might be?
48.
Okay, let's see. Can you talk me through? Yes. Okay, good. Because look, actually, this equation generates all of our possible a's.
That is exactly what I just did.
Good.
I just put in 2.
Yeah, because that's all it's happening. It's saying all that matters is that remainder of 10. So I can add any multiple of 19, because any multiple of 19 mod 19 is going to be 0. So as long as this portion is satisfied, I can multiply 19 by anything to get A. So let's see. What do you think, Sean?
No, I'm sorry. I know I didn't say anything, but I was
That's okay.
I was watching the whole thing, and I'm like, yeah, I get it. As soon as I looked at it, I saw, yeah.
Oh, good. No, that's okay. That's okay. I just wanted to check. So we could plug in -1. So take 19 times -1 and add 10, so I get -9. Right? We can go on and on and on. And this is one of my favorite problems, because you can't really use Wolfram Alpha or yeah, because you can solve these congruences with a lot of internet applications and Excel and blah blah blah. So, however, with the Chinese remainder theorem, there isn't really a good applet or online thing to solve those. So we still have the we still have that going for us. Let's see. Okay. Yeah, so let me just do one more exercise and then I'll let you guys go. Let's see. Okay, we're going to be combining a couple congruences here, okay? So I'm going to say A and B are integers, and I'm just doing number 14 from the text if you want to follow along. I know A is congruent to 11 mod 19, and I'm given that B is congruent to 3 mod 19. Okay, I want to find an integer C that is between 0 and 18, such that it satisfies a specific congruence. So I want C to be congruent to 13 times A mod 19. Okay. And to do this, we're going to have to know a few things about combining congruences. It's kind of like combining equations, you know? So I can add to both sides of a congruence and still maintain its truth value, you know. So like if 5 is congruent to 13 mod 8, okay, I know I can add 2 to both sides, and I know 7 is congruent to 15 mod 8. Okay, so that's one thing that I can do. I can multiply both sides by something. I can multiply, let's say, by 2. So 10 is congruent to, careful, we're multiplying and adding integers, okay? We're kind of moving away from real numbers at this point, so when you're in this unit, kind of always keep in the back of your mind integers, okay? I asked one of my number theory professors, you know, what, because the variable was not declared in the text, and I was like, what kind of variable is this? And he said, Kaylee, you're in number theory, it's an integer. But I still think that integer should be declared so that it's clear, and I didn't agree with that, but it's okay. So look, you know, we get a remainder of 2 here. 8 goes into 26, well, 24, so we get a remainder of 2. So it's still true, right? So we can multiply, we can add, we cannot divide, okay? Division causes trouble. There are special cases when we can divide both sides, but generally you want to, when you're dealing with a congruence, we're moving away from dividing both sides to the idea of multiplying both sides. And so what we're going to be talking about is multiplicative inverses within these different moduluses, sorry, and so instead of dividing, we're going to be multiplying and still having the same results. Okay, it sounds really funny right now and doesn't make any sense, and that's okay. We're going to get there, but just I want you to put in the back of your head that dividing both sides of congruence is not safe. And let me try to get an example here. I think there's one in the book probably, but I want to, let me see if I can think of one. So I want it not to be prime, I think. So I know that 32 is congruent to 42 mod 10, okay? And I'm not sure if this works. Oh, this will work, okay? Because both of those have a remainder of 2. I know that's true. Now, both of those are divisible by 2. Let's divide by 2. 16 is not congruent to 21 mod 10, right?
Yeah, I see that.
What's cool and what we'll see here, look what happens if we divide this mod by 2, okay? This is bad. Generally don't do that, okay? So because that congruence does hold. But just be careful, okay? There are specific conditions, and there are things you can do, like we just saw with the 5, but forget that. So we'll see that. I think it's in like section 4.3, okay? So just be careful with division is all I'm saying. Multiplication, addition, good, okay? And that's proven in the notes that I'll post, but I'm not going to go through it, I guess. But so let's go to this problem. We've got, well, I'm not sure if I quite set that up right, but those are important properties to hold. Because what I'm actually using here is just substitution, which should make sense, hopefully. Okay, so C is congruent to 13 times A mod 19, okay? So I know A is congruent to 11 mod 19, so it's okay to substitute, okay? If you know something is equivalent under the specific mod, right? We've got to be under mod 19. If it said like mod 8, it wouldn't make sense to plug in 11 there because we've got to be under the same mod, okay? So what I'm going to do is just plug in A equals 11, or A equivalent to 11. So instead of A, I'm going to write 11. So I want to find C such that it's congruent to 13 times 11 mod 19, okay? Alrighty. You want to know a trick about 11s? Have you seen this trick with 11s? Multiplying by 11? No? Okay.
Sorry, I have, but
you have, Colin?
Yeah.
Okay, cool. So tell me, Colin, what's 13 times 11? Quick.
I think it's 143.
Yeah.
That's just a guess.
No, it's not a guess. You split the numbers, right, and put the sum in the middle. And then, right? Okay, cool. So I know C is congruent to 143 mod 19.
So if they're both of the same modular, so you can just drop the other one's mod?
Okay, yes. But since we're putting it into another equation involving mod, we're not really dropping the mod, because that's a great point, because it wouldn't make sense just to write A equals 11, right? Because it might not. It just has a remainder of 11 after dividing by 19. So since, you know, this mod is still here, you're still pulling that mod in.
So like, as long as they have the same mod, they as long as their mod is the same, so they can like absorb each other, I guess. I don't know.
Yeah, you're on the right track. Yeah, I think you've got it. Yeah, they've got the same mod, so we can combine equations. You know, it's like 5 equals 7 and 2 equals 3. Well, no, 5 doesn't equal 7. 7 minus 2. Okay, shoot. And 5 equals 9 minus 4. So then I can say, okay, 7 minus 2 is equal to 9 minus 4, kind of is what I'm doing.
I don't know. I was looking at it kind of like you can only add or subtract fractions if they have the same divisor, right?
Yeah, that's a great idea.
Yeah.
That's a great,
So,
yeah.
kind of
Yeah.
same thing here. We're doing a division problem in reverse, which is why one of the reasons why we can't divide, right, is dangerous.
Yeah. Yeah, it's
So we're doing
dangerous.
a division problem in reverse, but some of the same rules apply. So this is almost like a divisor. We're talking mod 19. It's got to be the same. It still exists. It's just we're combining them.
Yeah.
No,
Good.
and that makes sense.
Okay, cool, guys. Good, good. All right, so now we had conditions we had to satisfy on C, though. We had to make sure that C was in between 0 and 18. So actually, we're not quite done yet. It is true that C is congruent to 143 mod 19, but we want C to be between 0 and 18. So basically, all we have to do is take 143 mod 19. So I think it's a good practice to get some quick calculation in your toolkit, you know. So either, you know, try to open up Wolfram Alpha, or try to open up Excel, because I think the command in Excel is equals mod parentheses 143.19, okay? In Wolfram Alpha, all you have to do is type in 143 mod 19, and it'll spit it out at you. Do either of you have that open? And so you could tell me what this is? 19 is.
Sadly, I'm running on a Mac, and I have a virtual machine with Windows that has Excel, but it would take a minute to open it. So
Oh,
I can
no,
do
it's
it real
okay.
fast.
You can, Sean, try to get to Wolfram Alpha. See, have you been to that site before?
no.
Okay, super handy.
Oh,
I
you're in
know
for a
this is a
treat.
this is a big moment. It's really cool. Okay, so let me make sure.
Definite integral calculator.
Well,
You can
Wolfram
type in any math equation, and Wolfram Alpha will simply do it for you.
Yes,
It's great.
yes. But no work. If you pay, they'll show you the work even. So.
No, you get 3 free ones a day.
Oh, are you serious?
Yup.
Oh no, I thought you had to pay. Oh, Colin, you know these things.
Oh, Avery showed me it the first day. He was like, I know you guys are gonna cheat, so here's a supreme cheating tool. And I was
Tool,
like,
yeah.
okay.
Oh, that's funny. Okay, so it's 10. Says Wolfram Alpha.
Yep.
Okay. Do you see that, Sean?
Yeah, I'm looking at the printout right now. I typed in equals mod 143 comma 9 in parentheses.
Oh, see,
No?
Wolfram Alpha
Oh
is
no,
just.
that was I did the Excel, didn't I?
Oh, yeah, that's okay. You can just type in 143 mod 19. You don't even have to. Yeah, it's super flexible with notation. So that's nice. And
Oh, I
input.
got it. It says input 143 mod 9. No, I didn't put in 19. My bad.
Oh, I might have said 9. I did 9 too when I first typed it in, but.
Okay, yeah, result 10, number name 10. I got a number line, a clock representation.
That's right. Wolfram Alpha's got it all.
Integers congruent to 10 mod 19. I see it. Okay.
Oh no, that's there too. Ah. Okay, I gotta work on this. All right.
Was I not supposed to say that out loud?
No.
Oh. Would you look at that? Oh, that's so great.
Hey, but Wolfram Alpha is not on your final exam, so maybe, hopefully not. But
That'd be too great. That'd be too amazing.
That would be, yeah. All right, guys. Well, I think I'm going to end on that today. That was pretty much just section 4.1. So I'll talk more tomorrow about 4.2 and 4.3, hopefully. And so this, yeah, we're going to build on these foundational ideas and go a little bit further. 4.2, we're going to be talking about binary and hexadecimal, and so we'll kind of, yeah, not spend too much time there. And then, yeah, so, okay. So how are your proofs projects going?
I wanted to work on them last night, but then my girlfriend put on Pitch Perfect, and I've never seen that movie, and it's pretty great.
Oh no.
So I'm going to hardcore work on them tonight.
Okay. Um, well, yeah, I'll be on tomorrow at 11 to talk about the next sections, and so if we needed to take, half hour to discuss the projects, that's a possibility too. Or if you have questions, you can always email me. But
Yeah, it's more along the lines of what I'll probably. I'm swamped this week. I got four of the
yeah,
finals, and one of them just started up and told me that we're sandwiching, 2.5 weeks worth of material in a single week per week.
right.
So yeah, I'm trying to time manage as best I can.
Yeah, and you guys know that these discussions are not required at all. I really appreciate your attendance and participation, though. But yeah, if you've got tons of stuff going on, you could even put this off until watching it Monday. Because the homework for this, I haven't written it yet, but it probably won't be due till Thursday or Friday next week. So you've got time to kind of, well, but hopefully now these ideas are absorbing. So that's good.
This is helpful.
Yeah, good, good. I'm glad you guys came. So,
Mm-hmm.
okay. All right. Well, yeah, keep in touch through email and I will talk to you guys soon.
Okay. See
Thanks.
you.
All right. See you guys.
Bye.